Where are we? We know how to solve x squared plus y squared equals n. We can do it for primes. And we know how to solve x squared minus xy plus y squared is equal to n. We know when there are solutions, when there are or aren't solutions. And also when there are, and how to find prime solutions. How to find prime solutions efficiently. Okay? What we have not, well, so there's a general question. General question. How about a general, let's stick to binary for a while, there's a lot to say. Binary, meaning two variable. Binary, i.e. two variable. So we have x and y. Quadratic form. So Q of x and y is the quadratic form a x squared plus b xy plus c y squared. And I think I already introduced this notation for a general quadratic form to write it just in terms of the coefficients. Does that make sense? Yeah. So we had, so for example, we had the form, this form x squared plus y squared, we would write as 1, 0, 1. There's no cross term. The coefficient is 1, then no xy term, and a 1. And the x squared minus xy plus y squared we would write as 1, negative 1, 1. Now there is a middle term. Okay? So what does this look like in general? How do we start approaching this problem in general? Well, let's play around. Let's figure out what we can figure out. So somebody give me write into the chat your favorite quadratic form. Give me some random numbers a, b, and c. And let's see how far we can get. What numbers will these things represent? All right. Okay, very good. All right. So here's a non-example. Very good. And well, it's an example. It's definitely an example of a quadratic form, right? Exactly, Dependra. That's exactly what the problem with this one is. So here's a quadratic form. X squared plus 2xy plus y squared. So this is the quadratic form 1, 2, 1. And Dependra has already explained what's wrong with this one. What's wrong with this to be a quadratic form is that this is x plus y squared. So in fact, what values will this quadratic form take? For which n is q of xy equal to n solvable. Exactly. Replace x with, I guess, x minus y or something, and leave y alone. So this is equivalent after a change of variables. So after a change of variables, maybe let me call it z equals x plus y and w equals y, we get a new quadratic form. Let's call this q1 in z comma w, which is z squared. Okay? And this is an invertible linear change of variables. Invertible, linear, z-linear, integer linear change of variables. change of variables. And so which numbers are represented? Which integers n are represented by z squared? The squares, exactly, perfect squares. So only perfect squares are represented. This Q is called degenerate. Why is it degenerate? It's not really a quadratic form in two variables. It's actually, it looks like a quadratic form in two variables. There's an x squared, there's an xy, there's a y squared. But it's not really a quadratic form in two variables. It's really a quadratic form in one variable with some linear change of variables. Okay? So it's degenerate because it's really only in one variable, not two. It's not binary. It's a unary quadratic form. How could we have, if we didn't know how to factorize this? I mean, you can imagine lots of other changes of variables that give really weird versions of the same thing. How would we know that they're all degenerate? Is there some robust systematic way to tell? Yes! Awesome, Daniel. Maybe Alex was saying the same thing. Oh, you weren't. What were you going to say, just out of curiosity? Irreducible, right. Well, the way to tell if something is reducible or irreducible, you see, if this thing is reducible, I'll give you another example in a second of a degenerate quadratic form. If it's reducible, right, okay. Let's go to what Daniel said. The degenerate ones are the ones with discriminant. The discriminant, let's call this d sub q, or just d, is of course b squared minus 4ac. And if that's 0, then the quadratic form is a perfect square. Okay? Now what's happening? You remember we had this discussion of quadratic forms versus quadratic polynomials. So if we take this quadratic form q, which was x squared plus 2xy plus y squared, and we convert it into the quadratic polynomial x squared plus 2x plus 1, in other words, set y equal to 0, set y equal to 1, then this factors as x plus 1 squared. So what does this parabola look like? If I graph y equals q of x, yes, at x equals minus 1, it has a double root, and it's a parabola, and it's an upwards parabola, so it does something like that. Exactly. Okay? So this is the degenerate ones. Now, there's another degeneracy. There's another degeneracy, which is, let me make up a quadratic form off to the side. Minus 3xy plus 2y. Okay, so here's another. So that was example 1. So this is a degeneracy because the discriminant is 0. Okay, has discriminant 0. So there's a double root, and it's just a complete square, and there's nothing to say. Example 2 is the quadratic form q equal to 1, negative 3, 2. What's wrong with this quadratic form? Nothing's wrong with it. Let's not judge here. Who knows what this form's upbringing was, but Very good. Very good. So this is the form x squared minus 3xy plus 2y squared. And if we look at the polynomial, so if we convert this into the polynomial, x squared minus 3x plus 2, you may notice that this factors as x minus 1 times x minus 2. Which, if we graph that, what does that look like? Well, it crosses through 1 and 2. Here's 1, and here's 2. And it's an upwards facing parabola. So there's your nice parabola. Nothing wrong with this parabola. It's not a double root. But if this is the factorization, this is for y, setting y to be 1, then the form Q also has a factorization, which is x minus y times x minus 2y, if I rehomogenize. So maybe we didn't see that immediately, but now you can see that if I take x minus y times x minus 2y and I multiply that out, I get x squared minus xy minus 2xy plus 2y squared. Dependro? You can unmute yourself if it's easier. Sometimes you guys have to write a paragraph and then... So if we write things as... Well, let's see. I see x squared plus bxy plus cxy plus d squared. But the bxy and the cxy you can combine into one thing. Yeah, you're asking a great question. What's the discriminant here? What's the discriminant of this Q? Why didn't take 10 seconds and everybody figure out the discriminant? Oh, I see. It won't necessarily factorize. If I put a 4 here instead of a 3, you can still write it in that kind of form. You'll see in a second. Right. You're very close. You're very close, Devendra. Did you guys work out the discriminant of this thing? What's the discriminant? One, right? 9. So this is negative 3 squared minus 4a is 1 and c is 2. 9 minus 8 is 1. Ah, what happens if the discriminant is negative? We're coming to that. By the way, what's the discriminant here? B squared minus 4ac. Negative 4. 3. How about here? What's this discriminant? B squared minus 4ac. B squared is 1 minus 4. 1 minus 4, negative 3. It's okay, typo. Nobody saw that. Right? So these are negative discriminants. So let's remember what... Oh, okay, I'll make that point in a second. So what's wrong with this quadratic form? Why is this one also, in a sense, degenerate? Why not write it like a matrix? We will write it. We will use the half Hessian in just a minute. Yukong, you're anticipating by 10 minutes where we're headed with this. But the question is, what's wrong with this form? What's wrong with this? Well, what do I mean what's wrong? We want to know what integers does it represent? What numbers does it represent? Okay, so does it represent 5? Let's see. Can we solve 5 is equal to x minus y times x minus 2y. I see. Dependra, you'll see a much easier way, instead of trying to find a way of breaking up. If I see x squared plus 5xy plus 6y squared, I don't know how to break up that 5 necessarily into 2 plus 3. But there is a way to see that that such a thing factorizes. And by the way, what if I have a coefficient in front of x squared? So there's something a little bit more general than what you're saying, but you're on the right track. You have a good nose for where to go with this. So can anyone think of a solution to this equation? How would you try to solve this equation? Well, what kinds of things are you thinking about? Exactly. Sriya? Yeah, same thing. Exactly. The whole point is, if the quadratic form itself factorizes, then anytime it takes some value, it corresponds to a factorization, a linear factorization of 5. In other words, our only options are, since 5 is 1 times 5, or 5 times 1, or negative 1 times negative 5, or negative 5 times negative 1, we only have 4 possible ways. Like a homework problem from the textbook that I assigned before. Okay, good. I don't quite remember which problem I assigned, but I'm glad I did assign it before because it's an important thing. But the point is, so either x minus y is equal to 1 and x minus 2y is equal to 5, or any of these other combinations. Right? X minus y is equal to negative 5 and x minus ... Here's one more. X minus y is equal to negative 5 and x minus 2y is equal to negative 1. So because we're doing number theory, factorizations interfere if they exist. Let's do one more example where a factorization exists and where the leading coefficient isn't 1. Okay, so one more example. So the point, do any of these have solutions? Well, maybe they do, maybe they don't, but it's completely trivial to work out whether or not they do. Right? You're just writing a number. So, let's see. The problem with this is that if you make a change of variables, if you notice, so let's make a change of variables. Q1 is as a function of z and w. Q1 of z and w. Let's make z equal to x minus y and w equal to y. I guess negative y, doesn't matter. So that's an invertible linear change of variables. Then q is the same as q1 under this change of variables. This is z. It's z times, this is z minus y. So I can always set z equal to 1. Set z equal to 1. And now I represent every number. Because I'm trying to solve 1 times 1 minus y equals 5. Well, that's easy. Y is equal to, minus y. The whole point of minus y is to call it w, plus w. So this is 1 plus w. So the whole point is this 1 plus w, well, w is, what's w? W is 4. So, Kevin, it's very close to what you said before. It's like the quadratic form xy. It's like, so this is, I mean, we could have made another change of variables to go from here to, this is also, after a change of variables, equal to, let's use different letters, u times v, where u is equal to z and v is equal to z plus w. And which numbers are expressible as u times v. All numbers, just set u equal to 1 and v equal to the number. The question is trivial, right? If equals n is solved by u is equal to 1 and v is equal to n. So if the quadratic form has a factorization like this, then the question of representation isn't interesting. Either it's completely degenerate and is actually just perfect squares, or it's completely degenerate in another way where it factorizes, in which case all solutions, all numbers are solvable and there's no question how to find a solution once you make some simple change of variables. All right, let's just see one more example. One more example since I just cooked one for you. One more example. To be slightly, let's see, Dependro, how your trick works on this one. 2x squared minus 7xy plus 3y squared. So here's our quadratic form Q. What's wrong with this one? Well, it's hard to tell what's wrong. Let's look at the, let's set y equal to 1. We get the quadratic polynomial 2x squared minus 7x plus 3. Anybody notice a factorization? Yep. 2x minus 1 and x minus 3. So as a parabola, this thing goes through what, a half and 3 or something? Here's a half, here's 3. It's a nice parabola, nothing wrong with it. Except again, yeah, exactly. It splits. It splits. So this also splits. Also splits. So is reducible. And we do not want reducible things because then the questions trivialize. How do we understand? So why is it reducible? Can we see that through some other invariant? I'm using a mathematical term that we haven't discussed or defined yet. Determinant, yes. Yeah, I guess, Dependro, for small numbers, you can find these decompositions just from checking, the same way that we found this decomposition. But if I give you large random numbers, there's going to be a lot of bare hand searching until you find a way to break it down. But here's a systematic way, which is exactly what you said, the discriminant. So what's the discriminant of this quadratic form? Gosh, negative 7 squared, b squared, minus 4 times a times c. 49 minus, what is this? 6 times 4, 24. 49 minus 24. 25. Which is a perfect square. So that's what's wrong with 0 and 1. 0 is really wrong. So determinant 0. So here's some definitions. If Q has discriminant equal to 0, then it's degenerate. It's really the square of a polynomial. If Q has discriminant a perfect square, then it splits. Then it's reducible. Then it splits or is reducible. Okay? So these are the discriminants that we do not want. The problem is not interesting in those cases. So if the discriminant is a square, does that mean we can split the middle term? If the discriminant is a square, that means, think about what that means. Let's go back to the quadratic formula. Oh, how do you tell if it's a square? If it's really huge, taking a square root of a number is still an easy process. It's still a polynomial time process because it's a process on the digits. You start guessing digit by digit. Give me a big number. I'll try to take its square root. Not too big. Okay, 1441. I don't know what the square root of 1441 is. Okay, so square root of 1441. I'm going to try to approximate it above and below. So I know that, let's see. Well, it looks like 20. Is it 20? No, it's root 2. But, gosh. What are some numbers near 1441 whose squares I know? So, 10,000 is 100 times 10. The square root of 10 is about 3. So I'm going to say about 30 squared. Yeah, 30 squared. So 30 squared gets me to 900. Whereas, how about an upper bound? 35 squared. 35 squared gets me... Yeah, 40 squared is going to be too big, right? 40 squared is... Okay, so here's, by the way, so here's all you have to do. Here's 30, and here's 40. So 30 squared is 900. 40 squared is 1600. And so I'm between 30 and 40, so I can try 35. And 35 squared, you guys know how to square numbers like 35? You square 30. This is 30 squared plus twice 30 times 5 plus 5 squared. And so that's 900 plus 300, 1225. Yeah, it's a binary search. And binary search is very efficient because in n steps, I've shrunk my range by 2 to the n. So I can very quickly find what the square root of a number is to large precision. And if that large precision reveals its integer square root, I'm done. So telling whether a number, the whole point is telling whether a large number is a square is easy. It's as easy as multiplying two large numbers. It's an operation on the digits. So it's in polynomial time of logarithm of the size of the number. Okay? This was an example. So this is an easy condition. This is also telling whether a number is 0 is not so hard. So if it's 0, then you're basically dealing with the polynomial x squared, which is not really a polynomial of two variables. If it splits, then you're really dealing with a polynomial like x times y. So again, the question isn't interesting. So we want discriminants that are not squares. Okay, so now give me some other random quadratic form, and let's see if we can start analyzing what we can say about it. So here's a random example. Somebody give me a random example. All right, that's not such a random example. It's a good example. Let me get another one and I'll come back to, yes, exactly, Devendra. X squared plus 3y squared. It's very closely related to the Eisenstein, as you pointed out. Give me a good random one. Good. I think that's a good random one. X squared minus 5xy plus 3. Here is our quadratic form. Okay. The first question we need to ask about this quadratic form is it definite or indefinite? Is Q definite or indefinite? Definite means, so definition, Q is definite if it only takes either positive or negative values. If its sign never changes. Its sign never changes. Like it's definitely positive or it's definitely negative. Of course it's 0. I'm missing a y squared. Of course it can be, you're missing a y squared. I copied from you. It's okay. You don't have to type it in. Of course, if you set x and y equal to 0, every form will be equal to 0 by setting x and y equal to 0. The question is, will this change sign or won't it? So how do we figure out whether or not it changes sign? We can take the derivative. I mean, it's actually pretty closely related to taking the derivative. There's an invariant that's kind of, I'm trying to drive home the fact that this invariant will answer very, very many questions for us. The discriminant. Okay, so what's the discriminant of this form? You gave us 25 minus 4 times 3. 25 minus 12 is 13. So what does that mean? That means if I look at the polynomial, if I look at x squared minus 5x plus 3, I know that it's an upwards facing parabola, but does it cross through the origin or not? Is it exclusively up here, or is it up here and down here? It's up and down because real roots. Exactly. The discriminant is positive. The discriminant is positive, and that means that this thing has roots. This polynomial factors as x minus alpha times x minus the Galois conjugate of alpha, where alpha is the root. We know how to solve this. It's negative b plus or minus square root of the discriminant over twice a. So it has these two roots, these two real roots, and they're real because the discriminant, when you take the square root, is real. So there's two roots. There's alpha somewhere here. There's alpha bar somewhere here. Alpha bar is the one with the minus sign. So there's alpha and alpha bar. And so your thing looks like this. And if the polynomial goes up and down, the polynomial is just if you factor out a y squared to make a change of variables or projectivize. There's a variety of ways of thinking about it. So this form will take both positive and negative values. Random question. 13 is 1 mod 4. Is that significant? It is significant, as we will see in just a second. Let's just answer the question. So this Q is definite or indefinite? Indefinite. Indefinite. Can someone give me values of x and y for which this is positive? E.g., Q of values of x and y for which is positive. Wait, I mean for this quadratic form. I don't mean give me a new quadratic form yet. I'll keep that quadratic form for later. But how about a value of x and y for which this quadratic form, I just want to check that indeed it is indefinite by plugging in some x's and y's and finding one that's positive and one that's negative. 0, 1, perfect. 0, 1, 0, 1. If I set x equal to 0 and if I set y equal to 1, I get 3. And what about a negative value? 0, 0 will always give me 0 because it's homogeneous. Yeah, 1, 1. Right. 1, 1. Maybe that's what you meant. 1, 1. If I have a 1 minus 5 plus 3, that is 4 minus 5. That's negative 1. Okay, so it's definitely indefinite. It takes both positive and negative values. Okay? And, all right. Let me answer Dependro's question, and then I'll come back to Kevin's question. So, what numbers arise? So here's a question. What numbers arise as discriminants? So remember, the discriminant of any form is b squared minus 4ac. And Dependro said he notices that we keep getting discriminants that are 1 mod 4. Or 0. So 0 mod 4. Yes, Daniel says numbers 1 or 0 mod 4. Why? So let's make this a lemma. The discriminant of any quadratic form is either 0 or 1 mod 4. Yeah, well, look at this thing mod 4. Exactly, Shreya. Exactly. D mod dq is congruent mod 4. There's a 4 there, so it's just b squared. B squared mod 4. And who are the squares mod 4? You take anybody, you square it mod 4, you can get 0 or 1. Pretty easy lemma. Okay, so we'll only see numbers that are 0 or 1. Does that make sense? And by the way, this is also why, let's look back at the quadratic formula for a second. If the discriminant is a square, yeah, I should have made this comment before. I meant to talk about splitting. If Q splits, i.e. the discriminant of Q is a perfect square, what are the two roots? Negative b plus or minus square root of d over 2a. Those are the two roots. But d is a perfect square. And so the two roots are negative b plus or minus little d over 2a. If big D is little d squared. And these are rational numbers. So if the roots are rational, that's exactly when the polynomial splits as a product of two linear. Implies Q is a product of two linear polynomials. Okay? Linear forms, not quadratic forms. Okay. Let's go back to Kevin's second example. Oh, we're out of time. All right, homework, exercise. Exercise, analyze from this point of view the quadratic form, what is it, 7x squared minus 2xy plus y squared. Is it degenerate? Is it, does it split? And is it definite or indefinite? And of course, the answer will be dependent on the discriminant. So what is the discriminant? Okay? Any questions?